So now we're moving on to this wonderful energy bar graph problem. We had this little car, little compressed spring there. So at position A, we have all elastic energy. And then when we get to B, we have a combination of gravitational and kinetic energy. So when we want to set up our equation to conserve energy, we'll have elastic energy equals gravitational energy plus kinetic energy. All right. If the speed of the train is 4 meters per second, and this is a spring constant, we want to know the compression x of the spring. So here we go, 1/2 kx squared. X is what we're solving for, by the way, equals mgh plus 1/2 mv squared. So exciting. Let's put in our numbers. 1/2 times 200 times x squared equals m, which is 0.25 times g, which is 10, times the height, which is 1, plus 1/2 times m, which is 0.25, times v squared. Now v is 4, so when we square v, that's going to be 16, because that's 4 squared. So when we simplify this, we're going to end up getting 100x squared equals 2.5 plus, when we work all this out, I believe it's going to be 2, but let me just double check that, because it is 2. Isn't that nice? So x squared is going to equal 4.5 divided by 100, so that when we get the compression of the spring, that's going to end up being about 0.2 meters. Well, that's really nice. How much energy was dissipated if the speed of the train at B was only 3.5 meters per second? So let's see. The original energy is 1/2 times 1 times 200 times the original compression squared. And that's going to equal mgh plus 1/2 mv squared plus E dissipated. And this is what we're trying to solve for. So we have here we're going to get about 4.4 equals, it's actually 4.5 if you're being careful, but that's okay. 0.25 times 10 times 1 plus 1/2 times 0.25 times 3.5 squared plus E dissipated. A little bit of calculator work to do here, so we get 4.4 equals 2.5 plus, let's do this one, 1.53. So we're getting about 0.4 joules as E dissipated. I rounded So there we go. And that is page 7.